All right, thank you so much, Janice, and thank you for that wonderful introduction. So as they mentioned, my name is Dan. I'm with the instrumentation team here at Illumina Technical Support, and today we're going to be discussing some run quality and best practices for the NovaSeq 6000 instrument. Let's go ahead and dive in. So really, today's objectives are to empower NovaSeq users to work through unexpected situations that may arise during run setup and run performance, as well as introduce NovaSeq users to resources that will aid in resolving these situations. So to start off, here's our agenda for the day. We're going to start off just by talking about some general information on the NovaSeq to make sure that we all have a good foundation. And then we'll move on to pre-run considerations, some run setup considerations, and then finally run in progress considerations. We'll wrap everything up with some resources and a Q&A at the end. So as general information, we're going to talk about the NovaSeq 6000 sequencing system, some pattern flow cell technology, flow cell types, sequencing specifications, and then we'll also compare the XP versus standard workflows. So some key features of the NovaSeq 6000, it will use pattern flow cell technology with two-color chemistry, and it's going to have cartridge-based consumables with RFID consumable information. It does have a pretty streamlined user interface. It is LIMS ready, and it also has ease of service with modularized hardware components to help limit downtime and speed up repairs. Now, the pattern flow cell essentially means that we are going to use nanowells that are ordered on the flow cell surface, and they have a defined feature size. And one of the major benefits of this is it's going to increase the cluster density compared to our non-pattern flow cells. Now, these pattern flow cells will use exclusion amplification, or XAMP, as we'll be referring to it throughout the presentation. And this will promote monoclonal seeding of the nanowells with a single template. From there, we'll also be using rigid registration to replace the template generation step, which will speed up data processing. Now, the NovaSeq 6000 has 4 different flow cell types with varying output levels, from the smallest SP flow cell to the largest S4 flow cell. And this is going to offer users scalability for smaller pilot studies all the way through to high throughput applications on a single instrument. Now, in addition to offering 4 different flow cell types, each of our reagent kits come in a variety of different cycle numbers, increasing our flexibility for the end user. Now, a quick diversion towards our NovaSeq reagents while we're talking about them. We did recently release our NovaSeq V1.5 reagents. And one of the things that we wanted to highlight here is that for the majority of our kits, we do have improved quality score specifications relative to our V1 reagents. So to close out the general information section, we'd like to take a moment to go over the 2 sequencing workflows that are available on the NovaSeq. So these are the standard workflow and the XP workflow. Now, the standard workflow is a streamlined operation with less hands-on time and an automated XAMP mixing on the instrument. So this workflow is very straightforward, where we will load a single denatured library pool onto an instrument and then start the run. The instrument will mix the denatured library with XAMP, deliver the template to the flow cell for cluster generation. Now, with this workflow, we will load the same library pool in all lanes, which is very similar to our other platforms that use onboard cluster generation. Now, in order to provide additional flexibility, we also have the XP workflow. With this, we are going to load different denatured library pools onto each lane. So with the XP workflow, the user will mix the denatured libraries with the XAMP at the lab bench and then manually load each lane with their library. With this, it can be very useful because we don't need a high amount of coverage per sample, and it requires less sample input. So let's actually start talking about some pre-run considerations during our run setup with our NovaSeq. So first, let's talk about NovaSeq control software versions. We'll have a short discussion of supported libraries, as well as the workflow library loading for the XP and standard workflows. From there, we'll talk about clustering on pattern flow cells, library diversity, and then some network and file paths. So the first thing we'll want to do is ensure that our software version that is installed on the instrument is compatible with the workflow that we're looking to use. So here's a very useful list of different control software versions that we have available to date, whereas most of our customers will be running version 1.6 or above. Now, with the introduction of the new version 1.5 reagents and the updated workflows that are associated with them, we have released the control software version 1.7, and this will provide all the necessary recipes for handling these new reagents. Now, for more detailed information on the changes that are associated with each of these versions, we have provided links to the release notes at the bottom of the slide. So as we just mentioned, we do have the new NovaSeq Control Software version 1.7, which does allow us to run the version 1.5 reagent. Now, these new reagents will provide a variety of benefits, including additional cycles to support unique molecular identifiers and unique dual indexing, as well as the introduction of a new 35-cycle S4 kit for low cycle count, high throughput sequencing. We also have, as we discussed earlier, the updated quality score specifications. We've extended the shelf life out to 6 months, and we've updated the indexing strategy. Now, finally, we also have native support for the new Illumina DNA PCR-free library preparation kit as well. As we discussed, we are changing how the Index 5 or the Index Read 2 is performed with the new version 1.5 reagents. So with our previous version, we were using the forward strand workflow where the I5 index is going to be primed off of oligos that are grafted onto the flow cell surface. And with this workflow, the I5 read is going to be read in the forward orientation. However, with the new version 1.5 reagents, we're going to be using the reverse complement workflow. So the strands are actually going to undergo paired end turnaround, and then once paired end turnaround is complete, we will be reading the I5 read. Now, this means that the I5 read will be read in the reverse complement. So when setting up our run, we'll want to make sure that our sample sheet has the I5 indexes in the reverse complement orientation for best demultiplexing results. So a couple more highlights on the NovaSeq Control Software version 1.7. One of the major features is it is user installable. However, we want to note that during installation, we'll want to restart the Windows computer, but we'll also want to perform a full power cycle on the instrument as well to complete the update. With the new control software, we've also updated the run page such that when we highlight each of the run metrics on the run screen, it will actually show a per lane breakdown, so we can get a little bit more granular information there. And like we said, we're also switching to that solution-based reverse complement workflow for Index Read 2 or the I5. And so that the sample sheet will need to have the I5 indexes in the reverse complement orientation. We do have a new version of Illumina Experiment Manager, version 1.19.1, and this does support generating sample sheets for V1.5 reagents automatically. And we've linked out to that below. So next up is some information on recommended library loading concentrations for the standard workflow on the NovaSeq. Of note, our guides will indicate the pooled loading concentration that we start with and the final loading concentration after all dilution and exant mixing steps. And we'll talk about that in a little bit more detail here in a minute. Now, of note, for customers that are moving libraries from a HiSeq 3000, HiSeq 4000, or HiSeq X series, we recommend a starting concentration of about 1.5 times the concentration that was used on these HiSeq series instruments, and then adjusting if further optimization is required. Now, in February of 2020, we split this information out of the NovaSeq system guide and collected it into a new NovaSeq denature and dilution guide, which is linked at the bottom of the slide. Now, it should be noted that as a general rule, these recommendations are for library inserts of around 450 to 500 base pairs. And we'll want to reduce the loading concentration for smaller inserts, while we can increase the loading concentration for larger inserts. Now, we also wanted to briefly talk or walk through the pooled library loading concentration and why this is a little bit different from the final loading concentration. So we're going to walk through how to set up a PHYX validation run. So to start off, our final loading concentration for a PHYX run is going to be 250 picomolar for an S4 flow cell. But what we're going to do is we're going to start off by loading 310 microliters of our PHYX library at a concentration of 1.25 nanomolar. From there, we're going to go ahead and add 77 microliters of our 0.2 normal sodium hydroxide, allow it to denature our library, and then neutralize by adding 78 microliters of 400 millimolar tris. At this point, we're going to load our library tube into the clustering kit and then get our run started. As part of starting up the run, the instrument is going to add just over 1 milliliter of XAMP solution to our library, which brings us to a final concentration of around 1,500 microliters and a final concentration of 250 picomolar. So now we want to discuss recommended loading concentration ranges for libraries when we're using the XP workflow. As we noted earlier, the XP workflow will use lower loading concentrations relative to the standard workflow. So if we are transitioning a library that has been optimized for the HiSeq 3000, HiSeq 4000, or HiSeq X series, we'll want to start it around the same loading concentration and use that as a baseline for optimization from there. And again, a lot of this information is provided in our denature and dilution guide that is linked out here. Now, as we saw in the last few slides, the NovaSeq standard and XP workflows can operate across a wide range of recommended loading concentrations for different library types. And this is because the standard workflow and XP workflow can run well at different loading concentrations, and every library is really going to find its own optimal loading concentration. Now, I'm including here one of our favorite technical notes, which discusses a lot of information about the XP workflow in general, but we wanted to highlight figure 6, which is shown here, so we can see how different libraries perform at different loading concentrations in the XP workflow, as well as how the TruSeq PCR-free libraries perform at different concentrations relative to the XP or standard workflows. Now, the big takeaway here is that we'll need to account for a few different factors when optimizing loading concentration. So let's take a deeper dive in how we actually can use some run metrics to find the right balance. So clustering on pattern flow cells, ideally, we'd love to see something like we have on the picture on the left, where we have a good variety of different templates, everything is monoclonal. But unfortunately, due to the chemistry, there's not always going to be this ideal situation. So what we actually get is there's going to be some amount of nanowells that are going to be not seeded with a template at all. We're going to have some where we'll have multiple templates, and then we'll also have, hopefully, the majority of them will have a single template, and we'll get some good data from those. So with pattern flow cells, the total number of flow cells that is reported as the raw cluster density is a set number. So every NovaSeq flow cell has a fixed number of wells, and so the cluster density for each run will be the same. So because of that, we would recommend using the percent clusters passing filter, or the percent PF, and the percent occupancy metrics when we're trying to review loading efficiency. Now, as a general theme, runs that are underloaded will have low clusters passing filter and low occupancy, and with high duplication rates in the analyzed data. Now, runs that are overloaded will have low clusters passing filter with high occupancy. So with that in mind, let's take a deeper look at this. Now, looking at the figure on the left, we can see that after clustering, nanowells will pretty much exist in one of three states, where they'll be either empty, occupied with a single template, or occupied with multiple templates. Now, empty wells will be listed as unoccupied, but they will also not pass filter. Wells that have multiple templates will be listed as occupied, but they will also not pass filter. So finally, nanowells that have a single template will be occupied, and they will typically pass filter. So now that we have a basic idea of what determines if a cluster passes filter, let's take a look at two different scenarios where the clusters passing filter are both 75%. Now in this section of the flow cell, we're looking at a fixed number of nanowells that is the same for both scenarios. And in the underloaded condition, the majority of the nanowells were seeded with a single template, but there are going to be a higher number of nanowells that are unoccupied. This results in the majority of the wells, occupied wells passing filter, though we can see that a single template has several duplicates. Now in the overloading condition, we can see that we have fewer duplicates and fewer empty wells, but we do have several polyclonal wells which will not pass filter. Now overall, both conditions show the same percent clusters passing filter of 75%. So how do we distinguish between these two conditions? To help distinguish between the underloading and overloading conditions, we'll need to also look at the percent occupancy metric. So the percent occupancy metric is the percent of wells that have one or more templates clustered in them and are therefore showing some sort of signal. Now in the overloading scenario on the right, we can see that we have fewer wells that are unoccupied, and therefore we will have a lower percent occupancy. In our overloading scenario on the right, we'll have, my apologies, I messed that up. So in the condition on the left where we have underloaded, we'll have fewer wells that are, we'll have a few wells that are unoccupied and therefore will show as empty wells. In the conditions on the left where it's overloaded, we have very few wells that are unoccupied and our percent occupancy will be very high. So remember, as a general guideline, underloading conditions will have low clusters passing filter and low occupancy, while overloading conditions will have low clusters passing filter and high occupancy. An additional consideration with pattern flow cells is going to be the template duplicates. So you may have noticed that in the underloading example, there are a large number of orange clusters sitting in adjacent wells. So these wells represent clustering duplicates, which are unique to pattern flow cells and result from the method that is used to cluster generation on the pattern flow cell. So when a pattern flow cell is underloaded, the clustering duplicate rate will go up, though this will only be apparent after data analysis. Because bioinformatics pipelines automatically remove duplicates before downstream analysis, underloaded pattern flow cells can have significant reduction in the number of clusters with unique templates and therefore the usable output of a sequencing run. So another thing that we'll want to consider when sequencing our library is how diverse is our library. And we have a great bulletin linked out on this page where this graph was pulled from. But we wanted to highlight that the NovaSeq does tend to handle low diversity library better than many of our other two-channel chemistry instruments. We do recommend a minimum of 5% if we are running a low diversity library, but depending on how low the diversity is, we might want to add more, maybe increasing it to 10, 15, or 20% while working out our optimal loading conditions. So we'd also recommend reducing the library loading concentration to target an occupancy about 20 to 30% lower than the optimal range to give the instrument a little bit more breathing room. Now, if we have any more questions about low diversity sequencing on the Illumina instruments, I highly recommend checking out our sequencing considerations for low diversity libraries webinar. Now, before setting up our run, it's ideal to plan out where that run data is actually going to end up. So the NovaSeq instrument must have an off-instrument output location, and we cannot use the local C or Z drives. Now, the instrument can output data to the cloud-based storage solution BaseSpace or a local network drive, or both for additional redundancy. So when setting a network output location, we do recommend using the universal naming convention or the UNC path rather than a mapped letter drive. And this is because the UNC path will help Windows prioritize data transfer, and it tends to have a more stable connection than a mapped letter drive. So now that we're talking about file paths, we wanted to take a brief detour and discuss a few key file locations that are useful for technical support if assistance is required. Now, the run output location will be where the instrument sends both run metrics information as well as the CBCL files that are the raw data from the run. Now, in addition to this, the instrument will keep a local backup of this data, and it will be split between two locations. The output folder on the Z drive will contain the raw CBCL files, while the NovaSeq temp folder on the C drive will have run metrics and cycle log information. Finally, the control software logs are also a great resource for investigating instrument performance. And it's important to note that these are only the backup storage solutions and should not be considered a primary data source for collecting run data. We also wanted to note that a few locations are going to be listed under the program data folder, which by default is a hidden folder. So if we ever need to collect any data from this folder and we don't see it, go ahead and click on View and then select the checkbox next to Hidden Items, and it should come right up for you. We also wanted to talk a little bit about Illumina Proactive. So this is a free service that collects run metrics data and instrument performance information and sends it over a secure network. Now, this service collects run metrics only and does not transmit any sequencing data or personal information. It's a useful service because it allows us to have quick access to run performance information that we can use to assess sequencing runs. Now, in addition to this, we also have algorithms that are actively monitoring these data streams and can be used to identify potential instrument issues before they become something more significant and helps us limit downtime on the instrument. If we want to activate Illumina Proactive, it is an opt-out, so it will be turned on by default. But if we ever want to toggle it on or off, we can go to the instrument settings and then select the checkbox next to Send Instrument Performance Data to Illumina. If you have any questions about Proactive, we have a lot of really amazing resources that will take a much deeper dive into Proactive and provide you those answers to your questions. So now let's talk about some run setup considerations, including the initialization, flow cell loading, reagent preparation, some pre-run checks, and then how to stagger start our runs. Now, the NovaSeq 6000 initialization is basically going to be a process where different components on the instrument are initialized and activated by the control software, and each component is actually associated with a specific percentage on the progress bar. Now, if we ever have an issue where the NovaSeq control software is not able to initialize, what we'll want to do is take note of the percentage at when it stops. From there, let's go ahead and power cycle the NovaSeq instrument and then attempt initialization again. If the instrument's able to initialize, we can go ahead and start our sequencing run. However, we would definitely recommend contacting Illumina Tech Support either by email or by phone to let us know that this happened, and that way we can take note of that in case it comes up in the future. Now, if the initialization is unable to proceed after a power cycle, please collect the NovaSeq control software logs and contact Illumina Technical Support so we can provide further assistance. Now, for many of the things that can come up during initialization, this is the workflow that we want to use. However, there are two specific scenarios where we want to change this up. And that's going to be if initialization stops at either 92 or 93%, or if initialization stops with an error where it says unable to communicate with UCS being the Universal Copy Service Program. So if initialization never stops at 92 or 93%, this is a laser warm-up issue. So the control software is verifying that the laser output is reaching a specified level, but it does require that the lasers kind of warm up before it's able to do that. Now, if the output isn't met during this time, it will stop at either 92% if we're running version 1.6 or 93% if we're running version 1.7. Now, if this comes up, we want to note, do not power cycle the instrument, because what this is going to do, it's going to allow the lasers to cool back down and it restarts the process. So instead, what we'll want to do is go ahead and close the control software, wait 5 to 10 minutes, and then restart the control software. If we ever have an issue where the control software presents unable to communicate with UCS, we'll want to make sure that we follow these steps. Now, the Universal Copy Service, this is the program that is going to mediate the transfer of run data off the NovaSeq to all output locations. And power cycling will not typically resolve this. So what we'll want to do is go ahead and exit the NovaSeq control software. And then let's open up the Windows Task Manager and confirm that the UCS.exe program is no longer running. From there, we can navigate to the C Program Data Illumina Universal Copy Service Runs folder. And let's go ahead and create a new folder, and we'll just call it Old Runs. And then all of the files that we have located in the Runs folder, go ahead and transfer them into that Old Runs folder. Once this is done, we can relaunch the control software, and this will automatically launch UCS and should hopefully resolve the issue. Now, when we're setting up our run and we are loading our flow cells, sometimes we might encounter one of these messages where the instrument presents that is unable to read the flow cell RFID, or there's a consumable loading error, or that the flow cell clamp or vacuum is unable to engage. So during loading an RFID reading on the NovaSeq 6000, it will first engage the clamps on the flow cell, center it, engage the vacuum, and then read the RFID. So if any of these steps are interrupted, the instrument will not be able to proceed with run setup, and it will present one or more of these messages. So here's what we want to do. First, we can take these 3 steps. Start by cleaning the bottom of the flow cell with an alcohol wipe. From there, we can clean the entire flow cell stage within the flow cell compartment with an alcohol wipe, and then wipe each of these down with a lint-free wipe to remove any residual alcohol. Finally, we'll also want to visually inspect the bottom of the flow cell for any glass shards or chips in the glass that might be preventing getting that good vacuum seal. Now, if this doesn't correct the issue, one thing that we can do is we can try loading a flow cell from a previously successful run, or try loading that S3 wash flow cell. These aren't going to allow us to proceed with the run setup, but what it is going to help us do is identify, is this something with the flow cell, or is this an instrumentation issue by using something that we know ought to work well? Now, if it's unable to load using a previously successful or washed flow cell, this would indicate something with the instrument. And what we would recommend next is go ahead and power cycle the instrument and then try reloading the flow cell. Now, if at this point we're still unable to perform the RFID read or flow cell loading, it might indicate that an engineer visit is required. So please reach out to Illumina Technical Support and we can provide some further assistance. I'll also note that we have a couple links here to a support bulletin as well as a short video on how to look at these as well. So very, very useful. So when we talk about cleaning the flow cell stage, we wanted to provide an image of the flow cell stage. And what we're going to really want to do is make sure that we are cleaning off this entire vacuum area surface, as well as paying special attention to cleaning out the grooves on the flow cell stage to make sure that there's no debris stuck in those grooves. You also note that we have the built-in remote diagnostic, or the BIRD, and this is something that we can also wipe off with an ethanol wipe very carefully to help make sure that we get a good read off of that. Now, if we do end up needing to have an engineer come out and service the instrument, we do have a couple other recommendations. So one, oftentimes we can try getting the run set up on the other side of the instrument, or if we have another NovaSeq, we can try to get it started up over there. If we're completely unable to get our run set up, we can refreeze the paired end reagent cartridge and SVS reagent cartridge up to 1 time. And then from there, our library tube can be capped and stored at -20 for up to 3 weeks. Now, some recommendations for our XP workflow. So timing is very critical after the libraries are loaded onto the flow cell. So one thing that we do recommend is confirm that the flow cell will pass the RFID check before loading our libraries. So we can set up a mock run on the instrument and try to load our flow cell. If it's able to perform the RFID read as expected, we can cancel run setup and then proceed with loading our libraries onto the flow cell and then with our actual run setup. This just helps make sure that everything works out smoothly once we've added those libraries to our flow cell. Now, another major consideration is the appropriate thawing and inverting of our reagent cartridges to make sure that they are thoroughly mixed. So before loading, once we've thawed our reagents, we want to mix them by inverting them at least 10 times. Okay? And this is a really crucial step because it ensures that we have a homogeneous reagent mix that is going on to the instrument. And if we don't do this, what can oftentimes happen is we'll see impacts to clusters passing filter, increased phi X error rates, as well as increased phasing, all in read 1, with typically some recovery in read 2. And we could see very clearly the difference between a SBS cartridge that was not mixed before it was loading onto the instrument and a SBS cartridge that is mixed as expected. Now, pre-run checks will basically go through and test various components on the system to make sure that everything is performing as expected and the instrument is ready to perform a sequencing run. And so we wanted to talk briefly about what we can do if there's ever any issues that come up during the pre-run checks. As a basic rule, for anything that involves the sensors or system connectivity, our first recommendation is to select the retry button that will come up. If the error is not resolved by retrying, what we would recommend is go ahead and power cycle the instrument and try setting up the run using those same reagents one more time. From there, if we have any pre-run check issues with disk space, what we're going to need to do is first identify, is this the local drive on the instrument or is this our network output location? Now, the process management tool that is built into the control software is the only way to clear out disk space from the local C and Z drives. However, if we have a network output drive that it does not have sufficient space, we'll need to manually delete those. So talking about process management, if we do need to clear space on the local C or Z drives, like I said, this can only be accomplished using the process management tool that is part of the control software. So to do this, open up the drop-down menu in the top left and then select process management. From here, we can safely delete previous runs that have completed transferring to our permanent storage location. The C and Z drives are designed to hold up to 2 S4 300 cycle runs. So depending on which size of runs we are performing, your mileage may vary on how many runs you can fit on the instrument, but we do recommend routinely going through and removing old runs that have been successfully transferred. So finally, let's wrap up on this particular section, which is reviewing stagger start on the NovaSeq 6000. Now, whenever we want to set up a run on one side, we have the option to set up both sides at the same time, or we can do a stagger start. However, there are going to be certain times during a sequencing run when we cannot set up a stagger start, and that's listed here. So during cluster generation, run start is not going to be available, and this is also the case with paired end turnaround as well as the automatic post-run wash. Now, during any of our sequencing reads, so read 1, index 2, or sequencing read 2, we do have the ability to perform a stagger start. So if we ever do try to start a run and we are in one of the times that it is unavailable, it will queue up the run start so that way once it reaches a safe stopping point, we can go ahead and proceed with our run setup. Once we complete run setup and start the run, it will automatically resume the run on the other side. So let's also talk about some things that can come up during runs while they're in progress. So let's talk about the component as failed, the failed defined fiducial, issues with data transfer, issues with clustering concerns, and then we'll wrap up with instrument maintenance. So the component has failed can occur when the instrument either can't communicate with a component on the NovaSeq or when that component isn't functioning as expected. Now, there are two times when the component has failed can come up, and that's at the start of a run, and the other is in the middle of a run. So let's start by talking about what happens when this comes up during the start of a run. Now, if the error occurs at the start of a run and we are only running one side, we can troubleshoot this. And what we would recommend is go ahead, power cycle the instrument, and then try setting up the run again using the same consumables. If the error presents at the very start of a run, oftentimes the reagents are not marked as used, so we can try setting them up with the same reagent. Now, if the error persists, definitely give us a call and we can provide assistance in troubleshooting that. Now, if the error occurs at the start of the run and we are running both sides and one side stops but the other does not, unfortunately, we will not be able to set up the run on the side that stopped. Now, what we'll want to do is let the other side complete, and then we can go ahead and power cycle the run. Once that's done, please reach out to Illumina Technical Support, and we can guide you on which logs that we'll want to collect to troubleshoot this issue. Now, if a component has failed, happens in the middle of a run, unfortunately, the run cannot be restarted. So if able, we'll want to allow the post-run wash to complete and then allow any other transfer processes to complete as well. From there, we can power cycle the NovaSeq and ensure that the instrument can initialize. We can collect the NovaSeq control software and run log to look at the issue and see if there are additional troubleshooting steps that are going to be required as well. Now, another thing that can happen is the unable to register the fiducial on the flow cell. This can present if the instrument is not able to register the clustered flow cell or clustered fiducial on the flow cell. And because it's a clustered flow cell or a clustered fiducial, it will have an issue with registering it if we have either a clustering or image intensity issue. That can be caused by things with the library, use error, fluidics, or temperature issues. We can also have this come up if we have a stage or optical alignment issue, as well as the flow cell manufacturer. So to troubleshoot this, what we'll first want to do is investigate the reagents. You can contact Illumina Technical Support and send over the runParameters.xml file. This will contain a lot of useful information regarding the reagent lot and serial numbers. We can see if there's any indications that there might be a reagent issue. To troubleshoot the instrument, definitely call technical support, and what we can do is we can review the alignment folder from the run. And what this can do is it can help us identify, is this look like a fluidics issue? Does it look like a library issue? Maybe a stage issue? And that can help guide which steps to perform in troubleshooting this issue from there. Now, if we do have to run the instrument system checks, they do take about 2 hours to complete all tests. So another thing that we can do while we're waiting is review the library and denature and dilution process. We can check the pH of our sodium hydroxide to make sure that it is greater than 12.5. We can double check the run setup to make sure that we have selected custom primers if we are using them, as well as review library quantification as well. Now, the next thing we'll want to look at is if we ever have any sort of issues where the data transfer status in process management shows as complete. And this is essentially when UCS is unable to transfer over all of the data from the local hard drive to either the BaseSpace or network locations. Now, troubleshooting this, what we'll want to do first is confirm that the network location is available by checking the File Explorer in Windows and then confirming that we can reach the network location. Now, if the run is completed, we'll want to power cycle the NovaSeq and start the NovaSeq control software, which will restart UCS, and make sure that the UCS.exe process is running in Task Manager. From there, we can go ahead and give it about 30 minutes and make sure that the run folder of the network location is getting larger, and that will indicate that we have files that are transferring. Now, if we do see that UCS is not running or we don't see that the files are transferring, what we can do is we can manually restart UCS by going to C, Program Files, Illumina, Universal Copy Service, and then double-clicking on the UCS.exe. If we really run into some persistent issues, we can also collect the Universal Copy Service logs and follow up with Illumina Technical Support to see if we can identify what the issue is. Now, one thing we did want to note, so we talked a little bit earlier about another issue that can come up with UCS during initialization, and we recommended creating an old runs folder. Now, we don't want to do that for something like this because with those, by moving those files, what it's going to do is it's going to interrupt the transfer process, and it can make that more difficult. So this will be a separate troubleshooting process. Now, we talked a lot about underloading versus overloading conditions and percent passing filter and percent occupancy. So what we want to do here is show how we can actually graph these using Sequencing Analysis Viewer to create a scatter plot that basically looks at percent passing filter versus percent occupied. And this can allow us to help differentiate between underloading conditions, optimally loaded conditions, and overloaded. So what we're going to do is in the SAV, go ahead and click on the Imaging tab, and then there's a Scatter Plot button that you'll see, and then click on that. It'll open up another dialog window. We can then select percent passing filter and percent occupied as our two things that we want to graph, and then evaluate the shape. So underloading is going to show a very strong linear response between percent passing filter and percent occupied. So it'll show as a diagonal line at about a 45-degree angle. Now, optimal loading, they'll tend to form an ovular cloud-like shape that will typically be in the top right corner of the graph. Whereas overloading conditions are going to show saturated percent occupancy, so it's going to have but low clusters passing filter, so it'll show a vertical line usually pushed all the way over to the right of the graph. Now, we do have a couple support bulletins on this as well as a video, so we would definitely recommend checking those out because these can be incredibly helpful in evaluating and optimizing our loading concentrations for our libraries. Now, next, we're going to talk about some maintenance procedures, so the maintenance wash and instrument shutdown procedures. For the maintenance wash, so we want to perform the manual instrument wash if we have any of the following conditions. So one, if the instrument has been idle for more than 14 days, if the instrument has not had a 4-lane run performed in the last 14 days, or the previous run ended prematurely without performing the automatic post-run wash. Now, best practices for our wash, we'll always want to make sure that we're using our fresh tween solution in lab-grade water, and that we also want to leave a used buffer cartridge from the previous run in place. So that's a really key note. We do need to use a used buffer cartridge for our maintenance washes. So we do recommend keeping a couple of those around. Now, we've talked a lot about power cycling the instrument, so we did want to discuss how to power cycle an instrument. And as a general theme, we don't need to power cycle the NovaSeq instruments unless we are actually troubleshooting them. So what we'll want to do is from the Control Software home screen, select the drop-down menu in the top left, and then select Shut Down Instrument. Once the screen goes blank, we'll want to switch the toggle the power switch on the back of the instrument to the off position, and then leave the instrument off for at least 5 minutes. So these instruments do have very large power supplies on them that can have a pretty large power reserve. So we want to give it at least a good few minutes to fully power down. Now, just some more NovaSeq 6000 best practices. As with all of our instruments, we want to use freshly prepared sodium hydroxide solution when we are doing our denaturation. And we do want to routinely check the pH of our sodium hydroxide stock to make sure that it is above the recommended 12.5. Always follow the recommended library quantification and QC methods for our libraries. And we can also consider pre-qualifying libraries prior to running them on our NovaSeq using our iSeq system. We do have this great method with the sequencing library QC with the iSeq system linked out here. And we do want to load the libraries very quickly after denaturation to avoid secondary structures from interfering with clustering. And then once the run is done, we can go ahead and leave the wash, flow cell, reagent, and buffer cartridges on the instrument for the next run. Whenever not in use, please keep the wash cartridges inverted. And it's best to leave the NovaSeq on at all times and really only need to power cycle if we're troubleshooting. And again, if we do have to run a manual wash, make sure that we are using freshly prepared tween and sodium hypochlorite, so bleach solutions for our manual washes. And then for our library pools, the XAMPP does really love short templates. So we want to remove things like adapter dimers and short insert contamination from our library pools because it can contaminate our run. So just a quick review of resources before we move into a Q&A session. So we do have a lot of documentation for the NovaSeq, including our system guide that has a lot of great information. We do now have the custom primers guide that will discuss setting up runs using custom primers, as well as like I said, that sequencing library QC with the iSeq system. That is a great way of pre-qualifying the libraries before we put them onto a larger scale NovaSeq run. If we're performing a XP run, we also have the XP workflow checklist. It's a very, very handy checklist that goes through all of the different steps and considerations. So that way we make sure that we set ourselves up for success. We also have the cluster optimization guide as well, and that does discuss the percent passing filter versus percent occupancy in a little bit more detail, and is another really great resource for that as well. So other resources that we have include some training courses. We have relevant videos as well that are put together by our service and supports teams, as well as our NovaSeq specifications page that does discuss expected yields, quality score specifications, number of reads passing filter to expect. This can be really great for helping to plan out runs as well as review how they perform. So we do have the following support bulletins website that will contain a lot of different troubleshooting and other information, including how to set up a 5X validation run, decontaminating instruments, plotting the percent occupied versus percent passing filter, runtime estimates, just a really wide variety of resources that can help us better understand the NovaSeq and the runs on them. Finally, for anyone interested in seeing what a data set actually looks like, we do have the following NovaSeq BaseSpace Sequencing Hub datasets that can be downloaded from the link that is down on this page. And this can give you a really great idea of what to expect from NovaSeq data with a variety of different library types and workflows. So these are another really great resource. So if there is ever any need to contact Illumina, you can contact us with the link below, and we can definitely reach out to you and help out in any way that we can. All right. So thank you so much for your time today. This brings us to the end of our session. It's been a pleasure to put this webinar on for you, and we can move forward with any questions.